Okay, so we're going to study this equation. So this is a non-homogeneous, like Sturm-Liouville problem. This is a Sturm-Liouville operator. F is an external function, and so we want to look at Green's functions for ordinary differential equations. So this would correspond to like taking the, if you have a PDE, taking the limit as t goes to infinity, so we have some sort of steady state solution. So we want to solve this differential equation right here. And we're going to use Green's functions. I'm going to show you two different ways to compute Green's functions. One in this video is kind of helpful theoretically, and then in the following two videos, I'm going to show you kind of very practical ways to get an explicit formula for Green's functions, for the Green's functions. So we have this equation here, and then we're going to say plus, I'm going to call this homogeneous boundary conditions, HBC. So this is the beta 1 phi of 0 plus beta 2 phi prime of 0 is equal to 0. And then beta 3 phi of 1 plus beta 4 phi prime of 1 is equal to 0. And whatever the endpoints are. So instead of 0 and 1, it could be A and B. But we have some sort of homogeneous boundary conditions. Now we're going to look at a corresponding Sturm-Liouville eigenvalue problem, which is L phi is equal to minus lambda sigma phi, with the same homogeneous boundary conditions. Okay, so sigma here is chosen so that this equation here, this is now a second order differential equation. You choose sigma so that it's sort of the best sigma that you can solve. So this is the equation that you're solving. You get to pick what sigma is. You choose sigma so that you can solve this second order differential equation. So for example, if p is equal to 1 and q is equal to 0, you would just choose sigma to be equal to 1. But maybe there's other choices of sigma that you can choose, because remember, typically for a second order differential equation with variable coefficients, you can't typically solve that like explicitly and analytically, unless the equation is of a very particular form. So for example, you might be able to choose a sigma so that you put this equation into a very particular form that you can solve. So for example, think back to Euler equations from your ordinary differential equations class. Maybe you can pick a sigma so that this now is an Euler equation, or something like that. Okay, but in principle, whatever sigma is, as long as sigma is continuous and positive, q is continuous, and p is continuous and positive, we're going to get a sequence of orthonormal eigenfunctions, and then the corresponding eigenvalues lambda k, like this. And what we know is that any function can be written as a linear combination, or not a linear combination, but a series of these phi k's, including our solution. So let's say we have a solution. Phi of x is equal to the sum k equals 1 to infinity ck phi k of x. So if we apply L to this, we're going to get L phi of x is equal to, okay, so what are we going to get over here? K equals 1 to infinity. What are we going to get over here? Well, if I do L to phi k, this is just going to be equal to minus lambda k ck phi k of x, because that's what it means for phi k to be an eigenfunction and lambda k to be the corresponding eigenvalue. Lambda phi k is equal to minus lambda k sigma phi of x. I forgot this, sigma. Okay, and the idea is that this is a solution to this differential equation, so this is equal to f of x. So I'm going to squeeze this together a little bit. Sigma of x phi k of x is equal to f of x. All right, so now we want to try to figure out what the CKs are. So what we're going to do here is going to be a very similar computation to what we've done before. If I look at the integral from 0 to 1 of f of y times vj of y dy, what do I get here? Well, if I just replace f of y with this expression here and change the x's to y's, I'm going to get the sum and interchange the summation and integration. k equals 1 to infinity minus lambda k, ck, and then the integral from 0 to 1, phi k of x, phi k of y. Make sure I'm doing everything correctly. I don't know why I did y's here. Phi k of y, phi j of y, sigma of y dy. I'm doing y's just because typically now when I'm doing this expressions like this, I'm just having this with the y instead of the x, similar to the previous video. Okay, now phi k of j, phi k and phi j. If k is equal to j, if k is not equal to j, that's equal to 0. If k is equal to j, that integral is equal to 1. And then so what we're left here is the sum here is only non-zero when k is equal to j, in which case we get minus lambda j cj. So we can solve this for cj, and we get that cj is equal to the integral from 0 to 1 f of y phi j of y dy over minus lambda j, like this. Okay, so if I take this, and it's also, j is just generic, so it could be k as well. We have something like this. Okay, if we take this and replace the ck's up here, here's what we're going to get. We're going to have the integral on the outside, y going from 0 to 1. We're going to have f of y. Then we're going to have the sum, k equals 1 to infinity, phi k of y phi k of x over minus lambda k dy. This is what we get. And this function right here is called the Green's function for the problem. Now, I'm not going to prove a whole lot of things about the Green's function, just sort of generically. But you can look at this formula, and you do see things like g of xy is equal to g of yx. So we have like this reciprocal property. There's other things that we can see as well. But there's several properties that g of xy satisfies, that the Green function satisfies, and because of those properties, it means that g is unique. So one of the things that I want to point out here is that there's only one Green's function for the problem. And when I say for the problem includes the differential equation for this differential equation, or this differential operator, and then the homogeneous boundary conditions. There's only one Green's function. The Green's function is unique, and it's given. This is one way to write it. This is one formula. Okay, now what happens if 0 is an eigenvalue? If 0 is an eigenvalue, this is not defined. If 0 is an eigenvalue, there is no Green's function. Okay, so for there to be a Green's function, 0 cannot be an eigenvalue. If 0 is an eigenvalue, there's generalized Green's functions. But if 0 is an eigenvalue, there is no Green's function. So that's what we're going to assume. We're going to assume that for our differential operator, which is given by this here, and the homogeneous boundary conditions, that 0 is not an eigenvalue. Okay, now in the next video, I'm going to show you some other properties that G satisfies. And with that, we're going to be able to actually get an explicit computate, like an explicit formula for G, at least for specific problems. Like for example, in the easiest case, when P is equal to 1 and Q is equal to 0, and we have Dirichlet boundary conditions, this is going to be a sum of sine of x, sine of k pi x, or sine of k pi y, sine of k pi x, divided by minus k pi squared. But that's not an explicit formula. We don't know what that sum is equal to. In the next video, we're actually going to get an explicit formula for g of xy, like where you can just plug in the x and the y value, not something that's in terms of a series here. So we'll do that in the next video.